So if we call one angle x, the other one is 5x, and the third angle is 90. Do you agree that those are the angles? The three angles in a triangle have to add up to equal 180. Okay.
Yeah, I just misheard you.
Yep. So we're going to learn a couple things related to that today. But do you have your 5-1 kind of notes out still? Awesome. All right. I did a very... We finished with... we're still in 5-1. We're going to finish up 5-1. There's a really, really, really important theorem in there that we need to talk about.
Did you already check the homework?
What's that?
Did you already check the homework?
I did not. I'm not going to check it today. I want to make sure we get through this. And
you have an extra copy of the 5-1.
I do. All right. Yes.
Okay. Oh. Jared, what are you responsible?
All right. I went through this proof. I'm not going to actually write it out. I'm going to do a verbal proof for you. Okay? So if you just want to watch, you can. If you want to challenge yourself, take what I say and turn it into your own proof. All right? This is not something that's going to be on the quiz. I'm just showing you why the angles in a triangle add up to equal 180. Let me say it again. Every triangle, the three angles add up to equal 180. It could be 1 degree, it could be 50 degrees, and then the other one, 180 minus 51, right? It could be any combination of three angles, as long as they add up to equal 180. So, here is my proof. I'm going to do it one more time. We talked about it at the end of class, on Monday, I guess it was. You draw in what's called an auxiliary line. Auxiliary line, all right? And when you draw that in, you create these three angles that add up to equal 180. They're not a linear pair. We called them a linear trio, I think, right? Linear trio. And help me out. Was it 2, 4, and 5?
It's 4, 2, 5.
4, 2, 5.
4, 4, 2, 5. So we can say measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 equals 180. Those are not the angles inside of the triangle. Those are the three angles that combine to make that line. All right? So then, because we drew that line parallel, we got to choose that we drew it parallel. So again, we're not going to write this out formally because of time, but in this statement, you would say draw line L parallel to AC. Okay? And you would have next to it auxiliary line. All right? That's something we've never done before. Do you agree 4 plus 2 plus 5 equals 188? They're a linear trio. We give a reason of a linear trio there. All right? Well, because of these parallel lines, 4 is congruent to 1. Measure of angle 1 equals measure of angle 4, alternate interior angles. Measure of angle 5 equals measure of angle 3, alternate interior angles. Okay.
How is 4 an alternate interior?
4 and 1.
Yeah.
So 4 is here. 1 is here. These are my parallel lines. This is my transversal. They alternate sides of that transversal, and they're on the interior of these two parallel lines. I agree, it gets kind of weird when it's triangles, because we always saw them with lines going on forever. Now there's segments that stop, okay? So what you're going to see now, Paige, you bring up a good point. This whole chapter, you're going to see this. You're going to see this, and the triangles we're going to be talking about are created there. If we are told these are parallel, then these angles are alternate interior and they're congruent. You're going to see this a lot. Prove that those two triangles are congruent. That's what this chapter is all about. Prove those two triangles are congruent. Well, it's going to be helpful to be able to say a pair of angles are congruent, right? Alternate interior. We're going to see that a lot. 5 and 3 are also alternate interior. So instead of 4, I could put in a 1. Instead of 5, I could put in a 3. That's called Substitution. So I would write my new equation, substitution. Then what? Oh, look. Measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals 180. What are those angles? Those are the interior angles of a triangle. They add up to equal 180. Did we do it for one case? Did we do it for one case? What's the difference between an example and a proof? Oh, look. This triangle has angles of 20, 60. What's 20 plus 60? And 100. Oh, look. Those angles add up to 180. Example. Did I do that? Did I do that here? No. I let 1, 2, and 3 be any angles. Did I give them a number? Not number like, did I give them a measure in degrees? No. So what did I prove? That those 3 angles, no matter what they are, add up to equal 180. Do you see that proof? Is it logical from start to finish? You could argue that with someone, couldn't you? McKenna.
So measure of angle 5 equals measure of angle 4. Is that also alternate exterior?
Alternate interior. Yep. All right, we did the homework. Now for the exterior angle theorem. Okay. I enjoy teaching geometry. There's also a very frustrating side to teaching geometry, and all of us teachers that teach it are frustrated right now. And I'm just going to be open and honest with you guys. It's hard because geometry is a dumping ground for math standards. Okay, and I don't want to get into this too much, but I feel like sometimes I could spend a whole day on a topic that's kind of fun, but we can't because the state of Ohio has thrown so many standards into geometry that are on the state test that you have to take at the end of the year. We will struggle to get through the content. There's 13 chapters. And at the very end, we learn about probability. If you were to ask any person that knows anything about math, if probability belongs in geometry, they'd say, that's ridiculous. Why would you put that in there? I don't know. And 30% of your test at the end of the year is probability. Why would you put that in geometry? So guess what? We don't have time to talk about some of the stuff that's really good about geometry. And it's frustrating. It's really frustrating for me. All right? And we're having conversations right now about, okay, how do we handle that? What do we do? Because I don't feel right, like, not talking about some of these really important geometry things just because we don't have time. You know what I'm saying? So probably more than you want to know, but just understand, like, we're trying to do our best to balance pace so that you get through what you need, but also quality so that you get, like, it explained well and get to experience it. And one of these examples is, and I bet you guys could figure this out. You're smart kids. Like, do you see that this triangle, this triangle has what's called an exterior angle? You see it? It's outside the triangle. I bet you could figure out this equation right here. Watch up here. Tell me the relationship between angle 1 and this angle right next to it. They're adjacent and form a linear pair, therefore they are supplementary, right? Add up to equal 180. With me? Tell me the relationship, and I'm not saying any of these angles in here are congruent. Don't assume that. Okay? So I've already used a single arc. I've used a double arc. Ready? Triple, and let's go for it, quadruple. Because I don't know that any of these are congruent. I don't know that. Are you ready? Let's name some angles here. We got 1, we got 2, 3, 4. Measure of angle 2 plus measure of angle 3 plus measure of angle 4 equals 180. We just proved that the interior angles add up to equal 180. We can assume it from now on because we just proved it. You just told me the measure of angle 1 plus the measure of angle 2 equals 1 plus 2, 180. What equals each other?
Measure 2, measure equal 3, measure equal 4 equals measure equal 1, and measure equal 2.
Okay, so ready? What do 3 plus 4 equal? Measure of angle 1. Do you see it? Who could explain that?
Substitution.
Preston.
So basically, if measure of angle 2 and then 3 and 4 equal 180, and then 1 and 2 equal 180, then you can basically just substitute.
Substitution, right? You guys see it? Oh, look. 1 and 2 add up to 180. Oh, look. Ready? 2 and these others add up to 180. These others must be the same as 1. Does that make sense? That's the exterior angle theorem. The exterior angle. So let's erase and let's discuss. You have to recognize this because we're going to start throwing x's in here. All right? The exterior angle of a triangle is equal to the sum of the other two angles not next to it. That's pretty unmathematical, but it's an easy way to remember it. The exterior angle is equal to the sum, of the two angles not next to it. The old book called them remote interior angles. Remote means far away. Remote control. Control TV from far away. All right, remote. Remote island. Far away. These two angles are far away from one. They're not the one next to it, not adjacent to it. They're far away. So this angle out here is equal to these two added together. Let's use that now, okay? Because right now, if you tried to do this with numbers, it would get to be a mess, all right? We have to, it's very convenient to use the exterior angle theorem. Here we go. What's the exterior angle? 2x minus 5 is equal to the sum of, well, the two angles far away from it, 70 and x plus 70, or 70 plus x. So we're going to solve for x. And by the way, when you read this on a quiz, I'm going to have someone ask it, so I'm going to address it now. When they say find the measure of angle JKM, JKM is out here, right? If you put 2x minus 5, you're going to get it wrong. If they say measure of, they mean actually solve for x, plug it in, get a value as an angle, okay? So here we go. Let's subtract x from both sides. We get x minus 5 equals 70. Add 5, x equals 75. If x equals 75, then the measure of angle JKM is 2 times 75 minus 5. What's double 75?
145.
Careful.
150.
150 minus 5?
145.
145 degrees. That's called the exterior angle theorem. It's going to be obvious because how many other times have we drawn an angle outside of a triangle? Never. So when you see an angle outside the triangle, look for the exterior angle theorem. And again, I mean, you could spend a lot of time on this. Actually, when I built our shop behind our house, like when you draw in a roof line and you have another roof line coming off of it, you find that exterior angle and you can cut all your trim pieces at that angle to make it match up well. Okay?
Wait, are we having a test on like this? Like what we just did? That? Are we gonna have to prove that if we have a test on that?
I haven't made up the quiz for it yet, so I haven't decided, to be honest. But we'll look at it and talk to Mrs. Wolf and we'll decide. Corollary. This is obvious. You guys know this. What do the three angles add up to in a triangle?
180.
What happens if you have a special case, all right? We see right triangles all the time. If you have a special case of a right triangle, that means one of the angles is 90. Well, if measure of angle A plus measure of angle B plus the measure of angle C equals 180, and one of the angles is 90, A corollary is like it's like a special case of a theorem. Okay? So here's a corollary to the triangle sum theorem. Let's make a rule. Ready? If this angle is 90, if we subtract 90 from both sides, we get the measure of angle A plus the measure of angle B equals 90. Oh, so this angle and this angle, how would you classify those angles? Acute, right, or obtuse? Acute. They have to be. Because if you already have one 90-degree angle, the other two have to be acute, don't they?
Yeah.
So guess what? We just showed a special case. The acute angles in a right triangle have to add up to 90. Why? Because one angle is already stolen 90 degrees. To add up to 180, the other two have to add up to 90. Does that make sense? Give me some combinations. 10 and 80. 20 and
70.
1 and
89.
any combination that add up to 90. Only for right triangles. All right? And what do we call two angles that add up to 90? Complementary. Complementary. The acute angles of a right triangle are complementary. Let's do an example. All right, we got x, we got 2x, we got 90. There's two ways to solve this one. Who can give me one way? Is this on your paper?
No.
What do you guys have?
We have.
Oh, 2x and x minus 6. All right, let's change it. 2x and x minus 6. There we go. 2x and x minus 6. Who can give me one way to solve this one? Olivia.
90 plus x minus 6 plus 2x equals 20.
That's one way. Who can give me another way to solve this? Using the corollary. Tally.
X minus 6 plus 2x equals 90.
Very good. Both ways are fine by me. And you can solve it from there, can't you? Is good? Just algebra from there. This one you'd get 3x plus 84 equals 180. I'll let you can solve it another time. That one you get 3x minus 6 equals 90. You're going to get the same answer either way. Oh, look, when I subtract 84 here, I'm going to get 96. Oh, look, when I add 6 over here, I get 3x equals 96 also, right? Same way. Awesome. All right, into 5.2. Into section 5.2, which is called congruent polygons. Congruent polygons. So again, we're going to have a little bit of homework from 5.1. I really cut back what was on there yesterday. Remember how 2 days ago we took what was going to be the rest of it and we moved it to another day? I even cut that down. All right, I cut that down. I cut down some of 5.2, and that will be your homework for tonight. All right, the biggest idea here, and I bet this isn't much of a stretch for you. If I'm going to show two polygons are congruent, do you agree I'd have to show all the corresponding parts of the polygons are congruent? Meaning all the angles and all the sides have to match up exactly to be congruent. Do you agree with that? Let me say it again, in case you're zoning out. Huge idea. If two polygons, triangles, quadrilaterals, pentagons, hexagons, I don't care. If two polygons are exactly the same, all of their angles and sides have to match up perfectly. Right? Okay. Congruent. Now, the things that go together, single arc marks, double arc marks, tick marks, so forth, the things that go together are called corresponding. That word is not the same corresponding as when we drew them on parallel lines with the transverse. Remember the corresponding angles were congruent? That word is different than this corresponding. Okay? Corresponding means to go together. So say we have a spirit day and we have twin day. Twin day. All right? And let's say that Ryan and Preston are they're gonna twin it up. Okay? Everything is the same, down to the shoelaces. All right? So we could say that their shoes are corresponding. Their shirts are corresponding. Their belts, I don't know, are corresponding. everything on their outfit is corresponding. It goes together. Right? That's the word corresponding. This word corresponding was used for the location on parallel lines and a transversal. They were corresponding angles. They also go together. I agree they go together, but it was a different context. It wasn't talking about triangle congruence or polygon congruence. It was talking about, well, even if the lines weren't parallel, they were still called corresponding, weren't they? Even if the lines weren't parallel. Corresponding. Different context. So if I look up here at this picture and I say, look at triangle ABC and triangle DEF, what's the corresponding angle with angle A? Mackenzie, what do you think? What goes with A? Over here.
D.
Let's check it out. A has a single arc mark. Did you say D?
Yeah.
D. Perfect. Single arc mark. A goes with D. B goes with E. Segment AB goes with segment DE, and we have to say it that way. I'm going to say it again. Listen carefully. If I call this segment AB, I started with A, which has the single arc mark, and I finished with B that has the triple arc mark. I have to go over to this picture. I have to start with D and go to E. That order is important. AB is congruent to DE. I will count off if you say AB and then ED. It's for your own good. We'll learn why later. All right? These triangles can all be named, the angles can be named with one letter. Do you remember how earlier in the year we named angles with 3 letters? Angle CAD, or whatever it was, right? Are we doing that?
Yeah.
We can do it with one letter because they're just on their own. If there's overlapping or there's more than one angle at a vertex, we have to name it with 3 letters. And again, the order of the letters is important. They even color-coded it for you there. Let's do some examples. Write a congruence statement for the triangles. A congruence statement. Here's what a congruence statement is. It's triangle blah, blah, blah is congruent to triangle blah, blah, blah. We have to get the order correct. Now the first triangle, it doesn't matter what order you use. Is this your first? Is this one on there? Awesome. For the first one, it doesn't matter what order you choose. I could call it JKL. I could call it LJK. I could call it LKJ. I don't care. Emma, start us off. What do you want to name the first triangle here?
JKL.
JKL. JKL. Now, as soon as you did that, you set the order for the second triangle. Preston.
Can I use those?
Yeah, go for it. You set the order for the next triangle. Elizabeth. What angle has to go first in the second one? If Emma picked J first over here, what angle do we have to put first? T, perfect. T. Y, double arc mark, double arc mark. Then Emma went to K. Well, K has a triple arc mark. So Caden, which one over here do we say next? S, and then obviously R has to go last. That is the correct congruence statement. Congruence statement. Next, identify all pairs of congruent corresponding parts. Are you ready? Sides, angles. I did that for a reason. We don't need the picture anymore. If our congruence statement is correct, we don't need the picture anymore. Ready? Angle J is congruent to angle, my goodness, it's glitchy. Sorry, this is really glitchy. That's an angle symbol. Angle J is congruent to angle T. Angle K, congruent to angle S. Angle L, congruent to angle R. Perfect. Done. Done with angles. Sides. JK. Put a segment above it. Segment JK. Congruent to segment TS. Segment KL. Congruent to segment SR. And segment JL. Congruent to segment TR. Do you see why I didn't have to cover up the triangle, but do you see how I can do that whole process without the triangle? Okay, now let's look at the triangle and compare our answer. Okay, I went from J to K. Now here's how you do it with the picture. J to K, didn't I go from double arc mark to triple arc mark along this segment? So over here I have to go from double arc mark to triple arc mark, T to S. That's the problem. Do you see how these triangles are either reflected or rotated, or they're not side by side lining up the same direction? So you have to borrow the correct order. Okay, borrow the correct order. So if I want to name this side right here, this triple arc mark side, JL, then here's the triple arc mark over here, but I have to go in the right order. If I say JL, I go from double to single. Over here, I have to go from T to R. Again, borrow the congruent statement order. It will help you. Make sense? Awesome. All right. We're going to actually, I don't know if we want to skip this one or not. No, let's do it. Find the value of x. All right. Well, I see an x up here. QR is 2x minus 4. You see it? QR is 2x minus 4. QR, watch up here. QR goes with FG. I'm not going to look at that picture because I'm afraid that I'll see it wrong and do the incorrect order. Okay? So I trust the congruence statement. I know QR goes with FG. QR goes with FG. So I'm going to set 2x minus 4 equal to 12. That's their congruent parts. Add 4. Divide by 2. X equals 8. And that's what part A asked me to do. X equals 8. All right, next we're going to find y. Well, the only y I'm seeing up here is at angle Q. Do you agree? What angle goes with angle Q? Q goes with F. Q goes with F. So 6y plus x equals 68. Agree? And since we found x, x is 8. So 6y plus 8 equals 68. So 6y equals 60. So y equals 10. That was part B. Using corresponding parts of those congruent polygons. 1, 2, 3, 4. It's a quadrilateral. Corresponding parts of that quadrilateral. Don't call it a trapezoid. We don't know if it's a trapezoid or not. Next is a new trend in painting rooms. You're going to see this all over the place now. Okay? We're trendsetters. Aren't you going to paint your room like that? Pick a line, diagonal, change 2 colors on one wall. These are such stupid examples. Like, who would do that? Isn't that a stupid example? Paige, would you do that to your room? No. Would you, Olivia? Those colors, though?
Not those colors.
Maybe like gray and white.
Gray and white, you do that?
Yeah.
Trendy. All right. Here we go. Question for you. Well, first of all, you divide a wall into orange and blue sections. Cavaliers, circa 1980s. All right. Along segment JK, will the sections of the wall be the same size and shape? Same size, same shape. So they're really asking, are these two polygons congruent? Okay. Well, if we can show all the corresponding parts are congruent, then we can say the polygons are congruent. All right. What do you guys think? What should our first step be?
To add them each.
Say it again. Add them up to equal 180. That's for triangles, right? Do that here.
Take 2 and 3 are congruent because of alternate.
Okay. Here we go. We're digging deep. Back to chapter 3. Are you ready? 2 and 3 are called alternate interior angles. Are alternate interior angles always congruent? No.
Wait, so when you're pairing it to one is.
Are these alternate interior angles congruent? No. What has to be true for alternate interior angles to be congruent, Bryce? Lines have to be parallel. If the lines are parallel, there's a whole theorem that said if the lines are parallel, then alternate interior angles are congruent. If the lines are not parallel, alternate interior angles are not congruent. Paige, what do you think?
Consecutive. Alternate interior.
Oh, you're close. So Paige says, hey, look. I think this is what you're saying, Paige. Correct me if I'm wrong. Are you looking at these two angles? Huh?
I was looking at 2 and 3 still.
Yes.
2 and 3.
Yes.
No.
Sure, I'm looking at A and B. No, I'm looking at A and B. Yeah, definitely.
No, I bet you were going to have earth-shattering observations here.
But
Tell me about 2 and 3.
exterior angles.
Hold on a
Well,
second.
isn't one of the theorems if 2 and 3 are corresponding angles, then the lines are parallel?
If 2 and 3 are congruent, if those alternate interior angles are congruent, then the lines are parallel.
1 and 2 and 3, 4 equals
Also,
linear pair.
A, D, C.
I agree. 1 and 2 add up to 180. 3 and 4 add up to 180. But it could be like 2 and 160, 20 and 160. Another could be like 40 and 140. It could be different. Okay?
Consecutive same side for A and D.
Yeah. This book called them consecutive interior. We also said same side interior. Do you agree? If those are our lines and this is our transversal, consecutive interior angles are supplementary. Supplementary. Remember? If same side interior angles are supplementary, then the lines are parallel. Remember that?
Definitely.
So guess what? Guess what? These lines are parallel. Ooh! Now that they're parallel,
You can do opposite interior.
alternate interior angles are congruent. You have to have correct logic, guys. You can't say, oh, well, Mr. Westfall, we said those are going to be congruent. Told you. If you didn't get there with the right logic, it's not correct. Okay, and I hate to say that, but that's how most of life works. Okay? If you do a process, most of the time you're not going to accidentally get the right answer. If you have a real job that's complex, you have to show what you're doing through the process to either convince your boss that you did it the right way and it's going to be correct and it's going to work forever, or if you're the owner of a business and you have to, talk to the IRS about that you did everything in the right order. Okay, you got to the right solution for your taxes, whatever it might be. You have to use correct logic to get there. Okay. Oh, look. All of the angles match up to all of these angles. But there's one pair of sides that we don't know if they match up yet. Well, what does BC go with? A and D, or D and A. What's the only side that's not marked? In this quadrilateral and in this quadrilateral. Seriously. JK. Is it congruent in both? Okay, now, when we learned it the first time, it was like, oh, this is stupid. Why do we have to say this? Tally, do you remember it?
I was just gonna say something else.
Here we go. JK is congruent to, okay, ready? JK in the orange quadrilateral is congruent to, is it JK or KJ? KJ. Ready? If you don't see it, all eyes up here if you don't see it. Watch up here. Ignore the blue, only look at the orange. If I called it JK in the orange one, I went from double arc mark down to single arc mark. Yes? I went from J to K. Now ignore the orange and look at the blue. I have to start at the double arc mark. Where's the double arc mark in the blue one? At K, and I have to go towards J. They're like this. They're not like that. They're like that. They're on opposite ends of each other. Do you see it? So JK is congruent to KJ. Give me a reason if this is a proof why those two segments are congruent. Way back, beginning of the year, first couple weeks. Caden.
Reflexive.
Yes, reflexive property. Reflexive property. Oh, that's stupid, Mr. Westfall. AD is congruent to AD. That's obvious. Reflexive property. Yeah, but if you have to say that those two are congruent, you have to have a reason, and the reason is the reflexive property. A segment is congruent to itself. It's overlapping. Kelly.
So there's a between A and J. There's a hash or a what would you call
Single
it?
tick mark. Yep.
Yeah, a tick mark. And then K and C, there's a tick mark. Can't you say it's just the same distance from each side, and it's the same shape because of that? After proving it's parallel.
After proving it's parallel, I mean, yeah, I don't see any other way you could draw those polygons where they wouldn't be congruent. I agree with you. But as far as matching up the corresponding parts, we got the tick marks, we got the doubles, we got the triples, we got all the angles. I agree. There's no other way to draw it, but we have to have a reason for why that last pair of sides are congruent. But I agree with you. I think your logic is sound. All right. Hello.
Can we plug in our calculator?
Go for it. All right. So reminder, reflexive property, symmetric property, transitive property. All right. Third angle theorem. I think the third angle theorem is really obvious. Do you agree if two angles in one triangle match up with two angles in another triangle, there's no other way for the third angles to be different? Do you agree? I know half of you are listening.
I think 1/4.
Say 20 and 50 in this triangle. 20 and 50. 20 and 50. The third angles have to be 110 in both. The third angles have to be congruent. Okay? Big idea to close up with. If two figures are congruent, all their angles and sides have to match up. The corresponding parts have to be congruent. Okay? We'll start Monday with a proof, and then we'll get into 5.3. We got most of the way through 5.2. We're going to have to wrap it up on Monday. Again, the big idea for today, corresponding parts have to be congruent for the triangles to be congruent. There's no other way than to match them all up for now, but there's a shortcut coming. All right, put the homework up. It's on the Google slide already.
Monday. Because I had none of them done.
Same.
I got really angry at my one deleted, so I haven't. Like I got the whole stuff done and it looked really good. I usually try to make it look.
It's on the Google Slide agenda. I'll try to paste it here too. Yes.
You just make it so hard for other people to read.
Why would you talk about page like that?
It does kind of matter. Mr. Wood has to read it.
I think you look good on this ass.
Yeah, I'm sure you do.
Sorry, roadblock.